Hey guys, I would like to review a couple of these problems from the last test review because I'm going to let you redo the ones that were review material, not the ones from the last unit. You kind of have to take the grades you got on those. Ones from the last unit that were not great, and excuse me. I want you guys to have a chance to redo them because I think they're important. So we're going to start with number 5 here from the test, and it's this, and it's one of our definitions of the derivative. So we have two definitions. One of them looks like this. This is kind of the first one we learned. And this is like where h is some tiny number and f of x is some other thing. But this is not what that looks like. This is not as something approaches 0, it's something approaches 3. And this looks like a slope. If you plug in 3, as many of you discovered, you get 0 over 0. Which is undefined, which is non-existent, but that is not the right answer. So you have to remember that we had this definition for the derivative, that f prime at a, where a is some number, is f of x, f a limit, here's the limit, is the limit of x approaches to and so your job here, when you see an expression like this, is to identify the function. We're going to identify a, and then put these together and take f prime and plug a in, and you get like a number. Something. And that's what this is asking. Like the answer to this is going to be one of these three numbers. And usually you have to like decipher what f of x is. Like you got to be like, oh, what is f of 3? But this time they just tell you. F of x is this function. They just give it to you. F of x is the natural log of x. And the a you have to suss out from this thing, but it's right here, and it's right here, and it's right here. There's 3. So you can take the derivative of ln of x, which is 1 over x. And then you plug in 3 for x, and you get 1 over 3. And that's this entire problem. So the key thing here is to be able to recognize this definition. And then to figure out what f is, figure out what a is, and plug them in. So I don't think this one, again, if you know how to do it, takes 30 seconds. And if you don't know how to do it, you can sit and stare at it forever. So I recommend that you get used to that you figure out a way to recognize this definition. This one's important too. I'm not trying to deny the importance of this one. But these are two things that you have to be able to recognize. They're both equal to the derivative. Okay. So beyond the definition of the derivative, there were questions about continuity and differentiability on your test. This was number 8, and there's a picture. You're given a picture up here, and it's got some holes and some jumps and some things, and it says for what values of x between 0 and 12. Well, is f not continuous? So one way to think about continuity is like, can you draw it without picking up your pencil? And if the answer is no, then the place where you pick up your pencil is where it is not continuous. So if I'm drawing this graph, I start here, continuous, and like there's a little thing here, but I can still draw it. And there's a hole there. So here's one place it's not continuous. Then I keep going. I got to pick up my pencil again here because I just jump. But there's another place. This looks like x equals 7. And then if I keep going here, there's another place here where there's a hole, even though there's a dot, I got to jump my pencil again. So there's those 3 places. So x equals 3, x equals 7. So this gets you like some significant fraction of the points, like half of the points or something, just for writing down these 3 numbers. But then it says justify your answers. So you have to know why it's not continuous. And if you remember, for continuity, there were 3 requirements. 1, that the limit at that point exists. 2, that the function is defined at that point. And 3, that the limit and the function definition are the same. So I can tell you right now, x equals 3, this function is not continuous at x equals 3 because f of 3 is not defined. Like there is no f of 3. There's no dot here. There's no, it's not anywhere. It's just an open circle. So f of 3 is not defined, therefore it's not continuous. That's like kind of, if I think about my 2 rules, or my 3 rules, excuse me, I have the limit as x approaches a of f of x from the left. The limit as x approaches a from the right of f of x. That's the first requirement for continuity. Basically, it's like saying that the roads meet, if you remember our little analogy we used in class. Down a little. Second rule was that I said A is the point at which I'm trying to determine continuity. It has to exist. In our little analogy, that was like the bridge had to be there. There had to be a bridge somewhere. And the third rule was that this limit, which we decided existed up here, has to be equal to f of A, which means that where the roads meet, the bridge has to be. So this x equals 3 fails this second one, right? There's no f of A. There's no bridge. And if you look at x equals 7, when you come from the left, the y value is 4, but when you come from the right, the y value looks like 1. So this one you could say this isn't true because the limit as x approaches 7 from the left of f of x does not equal the limit as x approaches 7 from the right of f of x. And if you had just said something like the limit as x approaches 7 of f of x does not exist, either one of these would have gotten you credit from my perspective. I think this first one is a better answer, but they're equivalent. In the last one, the limit for x equals 10, the limit exists because, like, as you come from the left, y is approaching. I don't know. It's like it's a little below 1, but something right here. And as you come from the right, y is also approaching that same value, so the limit exists, and the function is defined, but those two are not the same. So it's number 3 that fails. So you could say something like the limit as x approaches 10 of x, which exists, does not equal. Like this limit is not equal to that value. So this would be all the points. And again, we studied this, so I think you guys should know how to do it. I'm going to erase this notes I made up here real quick. See it at the bottom. Scroll on back here. So the question here, part B, was where is it not differentiable? And one thing you may or may not remember, is that for differentiability, there are 2 requirements. So for something f to be differentiable at point A, whatever the point is, f must, it says most, but it says must. F must be continuous at A. That's the first requirement for differentiability. And the second requirement is that the slopes from the left and the right have to be the same. So you can't have any like sharp corners or like cusps, like this down here, right here at x equals 1 is looking like a place where the derivative is not going to exist. But the first thing is that it has to be continuous. The second thing is that the slope from the left and the right have to be the same. So for the first one, for where it's not differentiable, all the points from the beginning. You can just say because that is not continuous. And that was like, I don't know, this was 6 points. That was like 3 of them probably. Like 1 for saying all these points, and 1 for 10, and 2 for identifying the region why it's not because it's not continuous. Then the rest of it was about this place, where the graph's pointing. So you could say f of x is not differentiable. limit as x approaches 1 from the left of the derivative does not equal. You can see if you like kind of look at the derivatives here, like the derivative from the left is some positive number. This is a positive slope, and this right here is a negative slope. And so they can't be equal. And this is like the technically correct way to say y. So there's kind of, like I said, there's kind of two pieces of this. There's this part where you're like everything from the previous part. It's not continuous, it's not differential. All those check the box. And then that one other place where the graph checks that box. Okay, you can't say the graph is pointy. That's not enough. You have to say something else. Okay, last one. So this, I kind of want to leave this to you guys. Is it continuous? Well, you kind of do the 1, the 2, the 3. This is, does the limit exist? So you check the left side and the right side and see if you get the same number when x is 0. And then plug in 0 for the one that's equal to, and then you can confirm that those are all the same. I don't honestly remember. Actually, I think it's not the same. I can tell you it's not. But and like if this one fails, you don't have to bother with these. If that's a x from the left and f from the right aren't the same number, then you're done. But this one is like what I did here, because it says f prime and this is f of x, is I wrote like a piecewise function for f of x. Sorry, for f prime of x. So the derivative of the top is 6x plus 2. For x, plus 0. The derivative of the bottom, it's not all of the got, is 2b plus 2x. You may be like, hey, where did this 2 come from? The answer is the chain. If you don't know where that 2 came from, you can see the outside. Okay. And so now it says find the derivative when x equals -2. So that's a less than 0x, so I use this derivative. So 6 times -2 plus 2 makes 10. That's prime 3, because 3 is greater than 0x. This one, so 2e to the 6. So these are how you do these. Hopefully that helps. We're going to do these